Hello students, so coming to the continuation of ferroic materials. We'll first discuss about ferroelectromagnetics. Now, magnetoelectricity needs a biphasic surrounding to exhibit the behavior. So that's a biphase surroundings. The primary magnetoelectricity material becomes magnetized when placed in electric field and electrically polarized when placed in a magnetic field. So there are two types of magnetic materials. Ferroelectromagnetic materials. One is called the primary. In the primary one, we place the material in a magnetic field, it will get electrically polarized, and if we place in an electric field, magnetization will develop on it. This is the primary one. Whereas in the case of the secondary type of magnetoelectric materials, it is a slight change in permeability and permittivity. Since we know that M is equal to mu H and P is equal to, or I should say D is equal to epsilon E, which is the directory vector between the polarization. So there is a change in mu and E associated with secondary type of materials. Now the primary requirement for the observation of a magnetoelectric effect is the coexistence of magnetic and electric dipoles. It's coexistence of magnetic and electric dipoles. This is the primary requirement. Also in a magnetoelectric effect, the variation of electrical polarization in response to external magnetic field or induced magnetization in terms of external magnetic field is can be expressed as P is equal to epsilon E plus epsilon chi equal to psi epsilon E M H, and also M is equal to I M H plus I M E E. So if you look at that, there is a change from EM, now it is ME, and of course this is E, the usual one, and this is your usual one, and this will be MH. Susceptibility. These are the susceptibilities. So this This is the susceptibility. This is the electrical susceptibility, as we all know. This is the magnetic susceptibility, and interesting one is your Xij Em is equal to chi Me Ji. It means there are tensor quantities, and these are the mixed magnetoelectric susceptibility. The mixed magnetoelectric susceptibility. And this is expressed as this is equal to Em is equal to delta E by this is equal to delta B by delta H, and this is equal to delta M by delta E. So we convert it once again. M is equal to P by delta H by Me is equal to delta M by delta E, and also Xij Em is equal to X or chi Ji Me. This is equal to del square phi del Ei del H J, where phi is the thermodynamic potential. Following the equation in the vicinity of the phase transition, since if you're talking about the Curie temperature associated with both electric and magnetic field, electricity and ferromagnetic, ferroelectricity and ferromagnetism, and Curie temperature associated with the electrical part is equal to Curie temperature associated with the magnetic part and is equal to T. And so we can also say that Em is equal to Me is equal to P minus Tc to the power half. Now this discovery of magnetoelectricity was found in Cr2O3 chromium oxide from the product of magnetization and piezoelectric effect, and this effect of magnetoelectricity is dependent on the DC magnetization bias, dependent on the DC magnetization bias, let's call it as H0, onto which the AC magnetic signal is superimposed, onto which the AC magnetic signal is imposed. Let's call this one as H0, the DC bias. We'll call this one as H. Now, with increasing bias, with increase in the DC bias, that is H0, you get a magnetoelectric coupling coefficient. Magnetoelectric coupling coefficient mu alpha E, and it is equal to dE by dH at constant H0. So this alpha is first found to increase, which to maximum, and then decrease. So initially it increases, it reaches a maximum value, and slowly it comes down. This is the coupling coefficient. The coupling coefficient. Now, ferroelectromagnetic materials exhibiting the magnetic electric effect can be classified into, so FEM, we call it as ferro or FME, magnetic electric materials. They can be classified into single phase, or composites. Single phase materials are ordered structure. So these are ordered structure, and require the presence of either a ferroelectric or a ferroelectric or an antiferroelectric and ferromagnetic, ferrimagnetic or anti-ferromagnetic states. They actually show two-phase transitions. Show two-phase transitions. That is the electric part, that means either it's a ferroelectric or a ferroelectric or an anti-ferroelectric material. They, when at QD temperature corresponding to this electric effect, so TCE, they convert to the paraelectric material, and the same goes for the magnetic material also, whether it's a ferromagnetic or ferrimagnetic or antiferromagnetic. When applied the QD temperature in the magnetic field QD temperature, then it changes into a ferromagnetic material. So these two properties are common in the case of ferromagnetic material of single phase. That's what happens. Whereas in composite, of course, this is not the case. Composite, of course, is a combination of different types of material. So it takes different sublayers and ordered elective sublattices.